Welcome to the pre-recording of lecture 11 of MCS 572, an introductory course in supercomputing. So in this part in the course we have arrived at programming shared memory parallel computers. In essence, this is doing parallel computing on any computer because all computers are currently multi-core. So the main topic of this lecture is to introduce the crew of threads model. So, and I will do this with three different technologies. The highest level way of working is to work with Julia. So, and the code is quite short and very useful. Now, then it's also very interesting to look at what really happens. And I will then go to C and illustrate how to do a crew of threads with OpenMP. So OpenMP we introduced last time as a very good model for fine-grained parallelism. And then I will, in the third part of this lecture, introduce Pthreads. So Pthreads is the oldest technology, and I will get into how to use the implementation of a critical section. So in a way, I have looked into a tutorial on Julia, and it said, do not use locks unless you really know what you're doing. And actually, this course is intended to know what you're doing. So I will use Pthreads for that. Okay, let's get into it. So this lecture is meant to be self-contained. So we have started this course with multiprocessing and with message passing, where we essentially launch several programs. Program and process, they can be used a little bit interchangeably. A thread is one flow of instructions within a process. So a process can actually have many threads. Now, this has the benefit that all threads have access within the storage of the process. So they share heap, the static storage, and the code. But every thread still has its own registers and the stack. So this makes for a very flexible parallel model. So we can also go at a very fine-grained model. So in last time I showed that you can improve on a computation that takes milliseconds. With multi-threading you can still improve on that. With message passing, distributed memory, parallel computing, the communication overhead is too large, is already in the order of several milliseconds, if not sometimes seconds. So with multi-threading, one can do a much finer grained granularity. So that's the motivation to look at this. However, there is also the drawback. One has to be careful when memory is shared that only one thread can access certain critical data. So in a way, message passing, where we started with in this course, is still it looked a little bit awkward, the sends and the receives, but in a way every process had its own memory, so and could actually allocate and deallocate there. So in a way, multiprocessing or message passing required not as much discipline as if you got used to the matching sends and receives. So here is the logical view. So we have the information that is shared in memory between, so this is the picture of a single threaded process where we consider the heap, the code, and the static information. Then every thread, so we have registers and has its own stack. So here you see a process, one process that has 3 threads running. Registers are typically used for single variables, so you can think of a loop counter, for example. The stack is often seen for scratch space, but is also limited. So a couple of variables that are being used. The heap is for everything that is dynamically allocated. If you are going to use an array where the size is not specified at compile time, then that memory needs to be dynamically allocated, and that automatically belongs to the heap. So anything that is large, that is dynamically allocated, comes at a heap. So all threads have their own registers and their own local variables that come onto the stack. Okay, this slide is writing in words between what I was trying to indicate. So there is the important difference between the stack and the heap. The heap can handle any chunks of memory at any size, and at any time. The stack typically is by every thread has a fixed amount of memory that is available. And typically what goes in this, what goes on the heap or not, the programmer often doesn't have that much control, but you can say that local variables within a thread, they actually get onto the stack. Okay, so for our application, what will go on the heap will be the queue of jobs. So when we worked with message passing, we had one manager and several workers. We could still use that model with multi-threading, and in some sense there's always a main thread that runs through, but during the parallel part, the parallel region that we talked about in when we introduced OpenMP, you have multiple threads that work simultaneously. So simultaneously, they are doing a number of jobs. So, and the number of jobs here can not necessarily be a multiple of the number of threads. And this is also a dynamic model. We could assign statically which job will be done by which thread, but let's do this in a dynamic fashion. So there is no hierarchy. There is not a manager that is going to distribute the jobs to idle workers. But here we have that whenever a worker is idle, it will look into the current state of the queue. What is the current index? What is the current job that needs to be done? And it will grab that index, and the job counter will be incremented. And then this can be one stage in a pipeline. So you can have multiple crews of workers that are working on different jobs in the stage of a complicated computation. Okay, here we have a queue with n jobs. We will simulate this, so we will say that every job has a couple of seconds to go, and we will sleep in our simulation for that number of seconds. There are p threads doing the n jobs. So we could do this statically. So every worker, we could have as many queues as there are workers, and then every in advance. So that's the static work load balancing. In a dynamic way, the idle workers will do the next job. So there's only one shared queue, and the workers will actually get the next job. The third item is a hybrid. So we start with a static assignment, so every worker has its queue, but when the queue of one worker becomes empty, then the idle workers will start start looking to steal jobs from busy workers. So in this lecture, we consider the second type, where idle workers will grab the next job. Okay, so let's do this first with Julia. So with Julia, it will be a very small program. So in some sense, this is a long lecture. I have many slides, but that's mainly because I wanted to show 3 different technologies. So if you have to do something really quick with little code, then Julia would be the way to go. So here is a simulation. I generated 10 random numbers. So we've seen last time that you can do multi-threading with this environment flag. There is also the -t or the -- threads flag that you can use to start up the Julia system. So here I wanted, at the command line, I typed in -t3, and that means that there are 3 threads who will work on a queue of 10 jobs. So the jobs is an array of integers randomly generated, and the numbers represent the workload of each job. So we have at the very bottom, I have a sequence of 10 numbers, but the numbers in that array indicate which job got done by what worker. So I have 3 workers, so this is also a check on the correctness. So I should only see numbers 1, 2, or 3. And the workload, although it is defined here in the simulation in advance, it could be that this workload would still be determined while the program is running. So one could say that the very first jobs have a known workload, but then the remainder ones not. In any case, one cannot predict how long it will be. So this is a dynamic system, and as idle workers will grab the next job, you can actually hope for a close to optimal speed up if there is not too much variation in the job sizes. Okay, how to code this up? So here is essentially the hello world. So I have launched this with 3 threads, so I will see when it prints out that there will be 3 threads running. And then I have the macro threads for the loop. So that will essentially launch 3 threads, and every thread will print that they are ready. So this is kind of the hello world, the startup, the setup. We have workers that will print out this message, and we have 10 jobs. So the 10 jobs you see here, I have a tuple where I generate at random 10 numbers from. Okay, so now everything fits on one slide. So this is kind of the brevity of the code. And the key thing, which I will explain on the next slide still again in detail. So here we have now the job index. So it's initialized at 1. So at any stage, an idle worker, so at the very beginning, all the workers are essentially idle and they need to grab the next job. But of course, grabbing the next job, only one thread can do this. Because every job should be done by only one thread. So there is the atomic. So the atomic, if you declare, if you make a variable, so here I make a variable of type int, an integer number, and I initialize it to 1. And that will be my job index. So that is before the loop. So I have declared an atomic variable. And then what every thread executes, and actually this is done in an exclusive manner, so only one thread at the same time can execute the atomic add. So what the atomic add does, it does two things. It will return the current value of the job index, and it will increment the job index. So when the next time that this is executed, we will have gone from job 1 to job 2. So this guarantees the mutual exclusion of the access to this variable, and it also guarantees that here in this application that every thread will have a unique job number, or every job will be assigned to only one thread. So this is a while true loop. So if the job number, the current job number, is larger than the number of jobs, then the loop will end. Otherwise, the simulation will start. So the worker will print out that it will spend an amount of time on that particular job, which here is simulated by the sleep. And then the my job is a unique number. So my job will be, so the array jobs is shared by all the threads, but accessing that specific memory location, it's only one thread that will, well, many threads may do this, but they will only write to no two different threads will write into the same location, because the my job is different. Okay, so let me go to the next slide. So in essence, this is saying what was on the previous slide, but here I want to introduce the concept and the notion of thread safety. So a program is thread safe if the execution in parallel by many threads leads to the same correct result. So that is that is a much stronger requirement than when we started with message passing. So often in real life, it's the case that you have an existing program and you want to run it faster in parallel. Then running several instances of your program may still be the best, the first way to do this, because if you were during your program allocating and deallocating, and sometimes this is not really that explicit, you can have a function that is going to, as a local variable, it's going to declare an entire array of unspecified length. Then at that point, the heap needs to be accessed. And in some thread safe languages, this may result in a blocking. But actually, and so that's still the best thing that can happen. But if it's not blocking, then you can get into some very strange situations where both threads actually get the same address for the allocated memory. But even if it is blocking, you will actually not see too much parallelism. So here in this course, we start from scratch. So we actually are simulating these jobs. But if the jobs are executing functions, then the functions better also be thread safe. They may have local variables that are on the stack, but actually it shouldn't happen that the jobs are starting to allocate. So here what we have shown in the thread safe manner is that the job index is actually accessed at the same time only by one thread. So only one thread, not two threads, can actually do something with that value. Okay, so threads who cannot access this will be blocked, but you see here that the instruction that is done, so the atomic add, it's essentially only one instruction. In C, you can actually have the increment, the plus plus, and then also have the return of the value. So it can actually happen very efficiently. So what is done in this atomic variable, so it's actually a critical section as well. It should be one single instruction. Otherwise, there is not much benefit that you will see from the parallelism. Okay, so that was Julia. And with that, I have actually explained the main topic of this lecture. But let me now go to the OpenMP. So here is the sequential execution. So in OpenMP, we work with a parallel region where we have a sequential job, a sequential execution here. And here we also have the capital N, which might be a lot larger than the little n, than the number of threads P. Okay, so this goes to a C implementation. So what do we have? We have fixed value, which is the number of jobs. Then we have two references. So one reference is the index to the next job. And the other reference is the queue, which is here labeled by work. So we have 8 jobs, and here in this current state, the next job is job with index 3. So why is that now important? Because we can't really share values. So values are just constants. Here what we actually share are references. So we share the references next job and work. So the word reference is also widely used in Python. It's also actually used in Julia. And it corresponds to the more low-level representation of an address. So we can work with those addresses. They are also constants, so they are fixed at the beginning of the program. Also, the work queue is allocated at the very beginning of the program. So here is the C code. So we have this syntax, the star, and here you see where the allocation is done. So the picture above is realized by the 5 statements that are at the bottom of this slide. So we declare the constant 8. So the constant 8 is used at the last line when we allocate a contiguous sequence of integers. And the next job is assigned to the value tree. Although when we start our simulation, it will of course start at 0. Okay, so here is the picture. So in a way, even if you're not interested in C, it kind of gives a much better representation on what is really happening. So we have the shared data. So we have the now 4 identities, 4 items. So we have also the thread identification number. So the thread identification number will actually also be a fixed number. So we have the next job and the work. So we have 2 values. Actually, we have 4 values. 2 of those are integers. Actually, the other 2 are also integers, but we interpret them as addresses. So they're also values, but they are indicating where in the main memory the values, in this sense, the value of the next job, and then also where the first job can be found. Okay, how is this implemented in C? So here you see the definition of a tuple, as we would call it in Python or Julia. In C, this is called a structure. So we define a type, job queue, and you have these 4 values sitting in there. So why am I doing this now? Because I can encapsulate this. So I can build now a function that will take the jobs and that will take that reference in essence. So every thread will then have the 2 fixed values and will have the references. So why is it now important that we have the references? Because the references allow us to get access to that critical value, the next job. We can't really change a constant. So here is it then. We have 3 threads and we have 3 different constants, 0, 1, and 2 for the thread identification numbers. We have the constant 8, so that could be also a global constant. But here I have set it that the value is also a constant that is given with the information of the jobs. And then we have 2 references. So now you see that there is only one instance of the next job. So here that this is all pointing to that memory location that holds the value 3. So in that sense, sharing, every thread has access to the next job. It's not a direct access, but when one thread changes it, then the other thread can see it via this indirection. Okay, so this is the detailed memory picture. So then some syntax. So if we call our jobs the queue, the little queue here, queue is an instance, then I have 3 queues. Will have an array of jobs. So on the previous slides, I drew the 3, but now I have the thread with index 1, which will actually take the corresponding queue. So it looks like a lot of data is replicated, but actually 2 of those elements are references to shared data, to data that is shared between all threads. So we can, with the structures, so in a structure, probably should have emphasized this, every item had a name. So we had the ID, the NB, the next job, and the work. So you see the notation dot. So I can get to the value by the dot operation. Okay, so then comes the actual code. So I could write the processing of the jobs in this manner. So, and this is when I have only one thread. So it takes a queue of jobs. And in this do while loop, as long as there is still one job to do, it will get the next job. So here there's a lot of complicated syntax. So I indicated there was the queue dot q of I dot. Here the q is actually a pointer, so it's in the reference. So I could do star q dot, but that's a little bit inconvenient. Instead, I have the q arrow. I have the q arrow to get the value of the next job. So if the value of the next job is less, then it will be incremented. So the job to do is initialized to -1. If there are no more jobs, well, then that will stay to -1 and I will break out. Otherwise, we will simulate the work to do by sleeping. So this is correct code for processing a job queue by one single thread. Very complicated, indeed. But it's more into preparation of now the multi-threaded version. Okay, so now how does this go with OpenMP? OpenMP works with directives. So you have correct sequential code, and then you add directives to it. So with the job to do is actually, so the J is actually the index. So the job index or the next job, so it's a shared value. Any job can actually see it. So any thread can see the value. That's no problem here. But with the update, so here with the update, so actually I don't get the value here, I get the memory address, I'm sorry. So every thread gets the values, gets the memory address. And then in the critical section, so this is pragma OMP critical, then it will grab the current value and also increment it. So C is very efficient. So while I'm accessing the memory location and dereferencing with the star J, I can actually at the same time, so while I have the location, I can actually increment it after getting the value. So the plus plus can also come in front. That means that you first increment it and then assign the value to what is at the left. So C is a very fine language in the sense that you can do some very things very efficiently. So you can do things in one instruction. That's what I'm trying to say here. So this is the equivalent of what we were using with the atomic in Julia. So I mentioned in passing the locks for a critical section. Here actually making a critical section in OpenMP is also quite straightforward. So the instruction that you want to be in the critical section, you put into the so there are actually two instructions. There's also the test. So you don't want to test whether there is still a job and while another thread is still changing it. So there is the test. You really want to have the value at that point. So there's only, so both the testing, is there still a job? So if the value of the job index is, in our example, we had 8 jobs. So here, is it less than 8? So you also want to do this by only one thread. So you do not want to do this while another thread is changing the value. Okay, so it was a complicated construction to begin with, and the notation is still rather, so if this is the first time that you see the working with references and addresses in C, then it may be indeed is still convoluted, but I think you get the point that once you get into C, making a thread safe program with OpenMP is actually not that much work. Okay, so then here is the main program, or actually it's encapsulated into a function. So I have jobs, that was the pointer to the sequence of jobs. So here I have a job queue. So I will, for the number of threads, so NBT is the number of threads. So I will declare, so with the job queue here, queue NBT, I'm making actually the jobs for the number of threads. So I have one job queue, but actually now I'm duplicating it for all the number of threads. So I'm copying the thread number in there, so the number of threads, and I'm copying also the references. So this corresponds to the picture that was earlier. If you remember, I had three, perhaps I should, for purpose what I'm actually doing is this picture. So I have the jobs, that is the global variable, and then I'm making an array queue of three jobs queues. So that is what is done in this function. So here this is this instruction job queue, and that is the entire setup. And then there is the do job that gets executed in a parallel section, in a parallel region. So in a way, the setup is complicated, but in a way it's actually even easier than what we did with Julia. So the parallel region is actually calling the do job, and in this do job we have a critical section where we increment the job pointer. So by the way, this is a strictly functional implementation. You could also turn this into an object-oriented implementation. Okay, the main program sets the number of threads, makes the job queue, so that's another function, and processes the job queue. Okay, now I have about 10 minutes left for the Pthreads, and I should say that historically, when I was first teaching this course, I was entirely using Pthreads. So in a way, Pthreads, I can go a little bit faster because the setup was actually already defined for the Pthreads program. So I kind of worked backwards. So when I first started teaching this course, OpenMP was not yet the standard as it is now. Okay, so here is the Pthreads. So that's an abbreviation of the Portable Operating System Interface. So if you compile this, so you may have to compile with the -pthread. So a little bit similar to the OpenMP. So here in this lecture, I didn't really go into the ins and out how to compile this and run this. So we did this in the previous lecture. So with OpenMP, you have to make sure that you link with the OMP, with the libOMP, and also that you have the flag -f OpenMP when you compile. So with Pthreads, so it is with the Pthread. So here is the hello world. C allows functions, or actually C is a strongly typed language, except when it is not. So it allows to wipe out all the types with the void. So here I have a function that will take any argument, and that will also can essentially also return any argument. So here is the hello world from Pthreads. So I have one function, say hi, and that will get, so the argument will be an integer. So the argument is a pointer of type void, and when we are running this, so the hello world, the void value will be dereferenced. And the null is the null pointer, which corresponds to this void star. Here it is. So compile this and you get the hello pthreads. So we create threads this way. Here is the main program, which creates the threads. And creating the thread is also essentially launching the thread. So what do we have? So we have an array of pthreads. There are attributes that are defined. We will not be using it. So every thread has a unique identification number. So here the identification numbers are actually declared in this array ID. So we are going to pass the address of that array. So, and we are going to untype it, so with this void star for the specification of the say hi. Okay, so the threads are launched in this loop, and then there is a main thread. So if the pthread join would not be executed, then the program might terminate. The main thread is done and could just abruptly end the program. So there is the starting of the thread and then also the join that happened. So in some sense this looks not so strange if you remember the parallel regions with OpenMP. So threads were created, they ran, and then they joined the main thread. Here this is done a little bit more explicit. So if you actually really wanted to know how everything happened, well, here it is. We share data between threads, so it would be wrong to actually use directly the I, because the value of I changes every time. So when you create a thread, you want to really give the constant I. So actually I have to give as many constants because as the thread is created, it may still be taking a while the thread is actually active and executing. But in the meantime, the loop counter in the main thread may have advanced already. So the indirection with the array ID is necessary to make sure that every thread has a unique identification label. Now here I was using the numbers 1, 0, 1, etc. But here you can still be creative. So you can actually really give your threads now real names. There's nothing that prevents you from declaring strings so that the ID would be an array of characters. So in some sense, this is a more technical level, but also a more flexible level. So the names that we give to every thread, they are actually defined here in this ID array. Okay, so there is a three-step process. We declare threads. We also have to declare attributes. In this course, we actually are not going to use them, but they need to be initialized. Then we create the threads. So we have to give the address of every thread, the address of their attribute. then what they execute, and also the arguments. So as the arguments, what we will do in our application, we will give the job queue. So here you see a little bit the history why I was working with the job queue with OpenMP. So I was reasoning from the basic technical level, the flexibility that is given to you by Pthreads. So the three-step process. So this last step is an important step. Do not forget the pthread join. So in OpenMP this happens automatically. Here you need to do it. So in some sense it looks cumbersome, but you realize here much better what is going on. So even if you do not going to use Pthreads, it's useful to look at it simply to know what is going on. So I mentioned with Julia that I read somewhere that use locks only if you really know what it is that you're doing. Well, a critical section with Pthreads is implemented with locks or a mutex. So we will declare a mutex type. So initialize it. Then every thread will request a lock. Will be blocked waiting when that lock is not available. When it gets the lock, then it can, in our simulation here, it can then do with the job index what needs to be done. And then afterwards, it must release the lock. So you see that there are a lot of things that can go wrong. So if the lock is not released, then all the threads will get stuck. Okay, here is now the main program. So I'm recycling code from the OpenMP, or the OpenMP was actually recycling code from the Pthreads. So I have my sequence of jobs. The jobs are made, and then I'm starting the processing of the job queue. Here is the do job. The do job follows the same logic as we did, except that now I have to use the specification of Pthreads. So this is where the void comes in. So the arguments, I had the main job queue, and that main job queue is now duplicated among the threads. Okay, so here is now the do while loop, and you see, perhaps I should have indicated in red, you see the lock. So you see the do job is initialized to -1. So we assume that there is no more job. We request the next job. So the value is gotten. So we actually get the location. So it's a local variable. We dereference, and then we get the value and increment it. So that's the do job statement. There is a lot of, so here I put also the releasing of the lock inside the critical section. So this is a simulation for pedagogical purposes. You see that the break happens when the do job is -1. And then we have the job that is being done. Simulated by the sleep. Okay, I have 2 minutes left and I'm actually done. So the code for this will be posted. Here are some older references, so I should actually cite this because I stole some pictures from this guide. So you see, Pthreads is an old standard, but as some things that are around for a long time is sometimes a predictor that they will still be around for a long time. In any case, in this course, it's very useful that the C code allows me to define what really goes on. So the high-level Julia code has the advantage it's quick to use and it works, but if it doesn't work, you kind of are stuck. You don't really know what you did wrong. So in a way, in this course, we also try to understand what it is that actually is happening. I could perhaps show this by looking at the lowest level Julia code, but that would the advantage of using OpenMP and Pthreads in this manner gives you another language, another tool to work with. Okay, so some exercises. So we have done the Monte Carlo, so try to do with Pthreads. So we've seen this master thread. So all the programs are actually here with Pthreads. All the exercises are with Pthreads, essentially. In our second project, you are more than welcome to use Julia as well. So we have the Mandelbrot. So in the exercises, the default is Pthreads, but actually here it might be interesting to do this also with Julia. Okay, so I'm 1 minute over time, which is not that bad given the number of slides that I had. So there was only one thing that I wanted to illustrate, and I hope that I managed. So we have the dynamic workload assignment, or also the load balancing for multi-threaded programs. With OpenMP in the region, in the parallel region, OpenMP does it actually for us. We can work with an atomic variable in Julia, and actually also the Julia environment does it for us. With the p-threading, we actually are much closer to the operating system scheduling. So this is then the threads that are scheduled on the processor by the operating system. So we're very close to the system level here. Okay, thank you for watching. I hope this was interesting. This is not yet the finest level, so we go to tasking, both with OpenMP and in Julia in a later lecture. So this is still multi-threading.